Okay, now you probably have problems related to curvature, and you have a formula for curvature, which you apply just as mindlessly as you wish. That you need to, I think, understand it. Okay, and it's just simply this. There are a couple of things. If I'm moving around a curve, what happens to my unit tangent vector? At any instant, it's changing at some rate. Okay. And the rate of change as the unit tangent vector tells me what the curvature is. But only if I'm moving at unit velocity. Okay? Because the faster I move, the faster my unit tangent vector change, right? Okay, so the first concept is I want to say how quickly, but I have to really say at what rate. Okay, unit tangent vector is the RDT, which is the velocity, right? Over the magnitude of the RDT. I think that's the way the book is, right? So that's a velocity or the magnitude of the velocity, which then is an obvious unit vector in the direction of motion, right? Now, the reason we don't always talk about velocity and acceleration is your T parameter doesn't necessarily have to be time. As you know, if you've done the assignments, you know that it could be dRds, where S is your arc length function, just the integral from A to T, okay, of the magnitude of dr dt. Right. And we talked about that last time. And I did talk about it, but if S is that integral, and you do the integration, and you get a function of say T. So S equals some function of T. You solve that for T. Or sorry, yep. You solve that for T in terms of S, plug it into the parametric equations for given by T, and you got our arc length as a function of position. Does that make sense? It looked a little dubious, and maybe I mean, tell me about it. Tell you maybe don't. I didn't talk about that, but that's exactly what the book does. So the mechanics of it, you would have integrated an arc length, okay, from like A to T. And you would have got S equals some function T, this solve it for T. Did you do that? You should, yeah. So I expect you know that you did that, but why did you do it? Well, that's what I tried to fill in. Okay, I filled it in by waving my hand. But you just take that expression for T, which is now an expression in S, and plug it into X of T, and now you got X of S. Plug it into Y of T, and you got Y of S. You did that, didn't you? Okay. You did that on problems. Did you really know what you were doing? Well, the first time you do, you imitate. Okay. Then you think about what you did and why you did it and the overview. Okay. Well, anyhow, okay. So we could express this equals DRDS. Since this is a unit vector. Okay. Anyway. The point is, we can think of this as velocity. It's rate of change of position with respect to whatever our parameter is. Okay. Well, I'm going to be careless. I'm going to write this. I have proven this even to myself. There might be confusing example. So when you have to take the time to reason it out, I should have thought through that before. So I'm going to write this to be safe. Okay, well. It's the rate of change of your unit tangent vector divided by your velocity. Okay. Why do you divide by velocity? Because of what I just said. The faster you go around that curve, the faster your unit tangent vector is moving. Right? So you divide out the velocity. And then you can work out the fact that this does equal dt dx. So you automatically unit vector calculate on this side. Okay, so there's the whole idea of curvature. Now, what's a curvature of a unit circle? With a circle. Here we got a circle with radius A. And here we got look at our team here. R2 plus delta T here. And this angle in here is theta. So we have our unit tangent vector. Here. And our unit tangent vector here. I'm tempted to assume like I want to see this because it's like a complicated, but there's a step in between them. Okay, now we've got delta X. So what's delta S? Delta S is A delta theta. Yep. The definition of radian. And now, the unit tangent method brings up your delta t. Curvature, the derivative of t with respect to x. Curvature. That's an x. Says curvature is the rate of change of the unit tangent vector with respect to s. This angle here is also theta, because these lines are radial on a circle, so the angle between this and this is identical to the angle between this and this, because these are orthogonal to these. So your delta t equals delta theta. It's a magnitude to t equals 1. Derivative of dt with respect to the derivative of t with respect to s is a limit of delta t over delta s, which equals what? Well, the magnitude of delta t is delta theta. Delta s is a delta theta. And that's, as everybody does. That's the limit as delta t goes to 0, which I still need. And I'm putting my hands just a little bit when I don't mention the direction here. In the direction toward the center, because in the limit, this is an isosceles triangle with equal angles. So the angle between your delta t and your t vectors. Okay. Limit. What my sentence, so I have to say it again. This angle approaches a right angle, so the delta t becomes perpendicular to your t vector. Okay. That's in a convoluted sentence there. That's really all. So it's 1 over a. So we have this kappa thing. You have a formula for. It's just reciprocal of the radius of your circle. Now, if you're on some curve in space, like the Tolstoy's curve, and right here, this part of the curve can be seen as part of a circle. this radius is. First thing, the curve. Okay. This is the osculating circle. I just drew the meandering curve without thinking about where I'm going to take the oscillating circle. And it real well inside these because it was going to overlap the curve that way, even though it's not incorrect. Okay. There's your oscillating circle. Let's do a little bigger picture of that. Let's just say that this is now you've got a curve which kind of matches this graph, this point. So all this R of T hat, the T hat is the value of diameter T when your R vector is to this point of tangent. Okay. So now your A is 1 over tau. It's easy to see on a circle. Where is the center? And your unit mole. So can you give me a vector expression? Well, center, actually, the way I've drawn it, I've got this is the origin. Okay. So it's going to be that. Well, so in general, if your R is measured from down here, you'd have an R up in here, and a section out your R's here. Here's the origin, here's one R, here's another R. Here, you know, tangents is going to be the same. And then you have an R up here. And you have a vector here to here. So what's the vector from here to here in terms of a unit mole and here, what's this number? In terms of symbols we already have on the board. Okay, well, I think we finally got to the idea. Somebody suggested something about A. Yeah, that would be the magnitude of this vector because it does go from here to here. Okay, what is the vector? Is A in the vector? Oh, the vector is just A times M. Okay. So the order to this point, wherever you measure off from, I measured it from the center of the circle. But it could have been done from anywhere. You get yourself to that. From here would be R. plus A multiplied by M. If you're measuring off in the center of the circle, this is just zero. Zero, if you're at the origin. If you're measuring off from a different point, you might want to draw it out that way. It generalizes. Probably should have brought it differently, separately from this. But I wanted you to see this, I can do this, and hopefully convince you that the radius of the circle is reciprocal of the curvature of my density. Reciprocal of the radius of the oscillating circle. So there we go. Okay, so the oscillating circle divided. But the oscillating circle is just a circle of radius A about this point. Okay. So it would be two dimensions of the radius. And three dimensions of the direction cosine. So there's a picture of the oscillators. Okay, you can check out. I don't think the text goes into actually doing a example of the oscillating circle, but it's a neat thing and it's worth looking at. Okay, they have a link. I didn't click on the link, but I assume the link takes you something that gives you an equivalent explanation. I'll only give an example for the okay. So, you know, how does beta compare to T and all that stuff? Fairly easy details. Okay. Okay. Well, hopefully that gives you a better idea of what these formulas for the translated tell. Okay. Of course, what we have up here, what we have here, what we have here is the curvature. This way, this way, this way. Don't take the most convenient formula and fixate on it. Takes the one that makes the most sense to you. And just what I think is one that would tend to make the most sense if you just think about going around the curve. Okay, it's how quickly your direction changes with respect to how far you go around the curve. Okay, or how quickly your direction changes in time divided by how fast you corrected for your speed. Because naturally your direction is going to change faster if you move faster. Okay. What's pondering? Okay. Should have talked about that last time, but kind of lost track of what was in what section. My fault. I said last time I hadn't had a chance to look. We have R2 here. We have some point on the curve that occurs at some time t so that your velocity is dr dt. Evaluated whatever this t is. And that's tangent to the surface. If we want the unit tangent to divide this by its magnitude, got a formula for that, but shouldn't be the formula using in terms of velocity. Okay. I think in terms of rate of change with respect to the parameter, gotta think a little more, but it's still the same concept. Okay, here's RT. I kind of sketched might be an oscillating circle, we're not going to find it, but I take this dotted line perpendicular to the curve, or perpendicular to the tangent vector. Okay. And of course, the center of the oscillating circle will be there, but we're not going to use the oscillating circle. It just helps you point a picture of what's here. Okay. Now, if we're not speeding up, then your acceleration will be in this direction. Okay, or slowing down. If we're not changing speed on this curve, then you have purely centrifugal acceleration. It feels exactly as it would if you were going around this swing at this point, at this speed. Okay. Well, if you are speeding up, then your acceleration vector will have a component in this direction, which will take the centrifugal part of it, which is fixed by the velocity and the radius of the circle, which we have to calculate. Okay. And the acceleration in this direction. Okay. So give an acceleration vector off this way. So we're going to assume you're speeding up somewhat because I want to draw the acceleration vector out this way because there's less junk to interfere with than if I draw it if it's slowing down. If it's slowing down, acceleration vector would be out here. We still have the same centrifugal component, but the tangential component would be there. Okay. So what we have is we have an acceleration. Down, that's acceleration, that's acceleration. So that's, okay. Now, this acceleration is a component in centrifugal, which is perpendicular to your tangent vector. So we call this a perpendicular. Or a sub m normal to the curve, perpendicular to that point, or stay perpendicular in the same thing. And then here we have the a parallel or a tangent. I drew this a little bit too long. This vector should be parallel to this one. Okay, I'm not going to mess up the picture. This is supposed to be right angle, so this is supposed to be parallel to this. Not very careful to do that. Probably wasn't very careful if I did this. Anyhow, there it is. Well, if we calculated the velocity and the acceleration, then we know what this vector is. And we simply pick out this here. Yeah. Same vector we get here. I mean, we project back here and these are all right angles. I mean, this one has to be a right angle. I said this one is, and I said this one is, right? Whether it looks like it or not. All three of these are right angles, and so's this one. Now, as I said a week ago, we have done now the same. Okay. Except very briefly, just to quote it. This is an important picture. In parentheses, I got the two. This plus this equals this. If you didn't get this when I said it earlier, get it now. This is how you do it for John. You take the dot product of A with the unit tangent vector, or with the vector, unit vector in the direction of V, which is V over its magnitude, which is the unit tangent vector then. Okay. It's just A times the unit tangent vector, but I write it as A dot V over magnitude. And you multiply that, because this is just a scalar, that's just a number. Just tells you how long this vector is. And if it's negative, it tells you it's in the direction opposite this vector. Okay. If you want to confuse the whole issue, you write this as a formula that loses its meaning. By combining these into these squared, so you don't know that you have a unit vector or a unit vector there. So we've got to give you a formula that confuses you. It's easy to use, but it doesn't have a lot of meaning unless you understand the meaning. So when you look at it, you say, why did that V squared then? Well, it's kind of this. Okay. And then we multiply that by V. Why do you multiply by V? Well, because if you take one of these V magnitudes that's squared and put it into this, you got a unit vector, and leave the other one there where it should have been in the first place. You've got A dotted with the unit tangent vector. I understand that. It makes life easy. Gives you more power for using this. It's simply quoting a formula that you might get wrong, you might forget if you don't understand it. Okay. And there's more insight in doing this than using something to get to this. There's no insight. Well, there's insight in knowing what's going on well enough to know the formula. But the more you know about the formula, better you're gonna be able to solve the problem. Okay. Never said anything like that before. Have I? Okay. Your normal vector's gotta be perpendicular to B. So you do cross product, you get this. Okay? At least we got a vector that's perpendicular to B. Well. What about A cross B over the magnitude? Well, that's just his vector, cross with a unit tangent. Okay? That's magnitude of A sine theta. Why? Well, theta is the angle between A and B, right? So we put it in our figure. So right here is theta. And where do you see A sine theta here? Okay, so got an answer. Have to do a projection of this on that and the other thing. My advice is, if you've got a triangle, analyze it. Okay, it's a right triangle, it's really simple. It's not a right triangle, we got the law of cosines and law of sines, and if you have enough information, you can analyze it. You might just want to not do it, but think, okay, I know I can get this, this, and this, if I need it now, what do I really need? Okay, is any of that going to be helpful? Just throw that away. And give it some more thought. Okay. But it looks like magnitude of A sine theta. If this is theta, and I said that wrong, it's this. Right? So it's this. You talk about the projection. You misled me. Not that I really believe the answer. Yeah, theta's here, this is it, theta's here, meaning theta is here because it's an alternate interior angles and two parallels. We try to be something to connect the two. Really got to use that in a lot of places, especially if you, well, not especially, it's not any engineering. You got to understand the basic to make the things. Even more so if you're analyzing stresses in a material. What you could do is a mechanical or super. Comes up in order to magnitude. Okay, well, that has this side of the triangle. Well, it's all gone. Magnitude of this is in magnitude of your normal vector. So if you memorize the formula, your book gives you the magnitude of AM is the magnitude of this. Well, they probably put the whole cross product over the magnitude of B, which is the same thing. Okay. Yeah, it works. This is a pretty simple picture. After drawn it a few times, I thought through it a few times. It's worth knowing. Okay. It's likely to help you get more points at some point in this course, because there are things you think of that you wouldn't otherwise think of if you didn't understand this picture. You're also more secure in the formulas that you might leave out a square on or something like that. Okay? Make sense? It's worth deal. Let's just say x y is a square root of x squared plus y squared. What's the graph of f of x, y look like? Well, first of all, it's a function of two variables. So if you want to look at the graph, so let's see. And on our curve, we're going to have z, f, x, y. Y and x. But we're familiar with the idea of I'm going to do 4 square root of x squared plus y squared, so I can use integers and fractions. Okay. Z equals 0. Where and what is our curve? Well, where is the curve going to be located? Okay, it's going to be, our curve is y equals 0, right? But where's it going to be? Well, it's going to be in the x-y plane, so he's going to equal 0. So x and y are 0. Well, there it is. Okay. Stop. Yes. Maybe something else. Let's change my 4. 4. That's a change my solution. Equals 1. What do we get? What? Is it in the x-y plane? No, it's in the plane was equals 4. Z equals 1, right? So you got Z equals 1 here. Kind of drawn auxiliary x and y axis. X, Y. More than 60 up here. equals one here. There's a circle of radius 4. So we come out here. Out here, back here, and now we've got a circle. Got a dot down here, we've got a circle of radius 4. What happens? Delta z equals 2. Well, z equals 2. Got a circle of radius. Okay. Looks like it goes up linearly, 0 to 4 to 8 is equals z infinite, right? That's kind of hard to draw on here because your perspective is such that your origin is always going to be hidden. And this is going to expand out this way. So what we're going to do is we're going to express this thing first in terms of contour. Looking at this thing from above, there it is for z equals 1. Here's a contour for z equals 2. Here's a contour for z equals 3. So we're just going to get concentric circles. The radius increasing at a constant rate. Okay, it's just going to kind of look like a dot. What's the shape? Okay, so okay, in the XZ, if you bind this function to the XZ plane, we get z equals 1/4 squared of x squared plus y squared, but now in the XZ plane, y is 0, and this just becomes z equals x over 4. But since x can't be negative, because negative x is not the domain. Oh, wait a minute, x. Z can't be greater than 0, so x has to be greater than 0. The restriction is really that z has to be greater than or equal to 0. If it's x over 4, then it does follow that x is greater than or equal to 0. I kind of glossed it with that. And then that's easy. That's just the line through the origin and still coming forth. So again, it's kind of a shallow cone, and the cone's actually a solid revolution of these two lines. And nothing below the x-axis because of the restrictions here that we have to use when we explore. Okay. Okay. So we've got contour lines. We can do slices. We can get a picture. Okay. Now it goes off. What would we have? What would our contour lines look like? And what would our slices look like? No, you have to pause in time. Okay. We've got them before, we have a point of the origin for the same reasons. Well, actually, not exactly the same. There's because square root can't be negative. But that's redundant since what's inside the square root is negative. Okay, well, that's equals z equals 1. Now, circle got raised to square root of 2, right? Square root of raised to square root of 2. Meaning we can compare how big this circle is and how big this circle is. It's not twice as big as it was down there. It's only square root of 2, approximately 1.4 times, about 40% big. 1.4 times as big, 40% bigger. If z equals 4, get a circle of radius 4. Well, pretty easy to do constantly. Let's skip z equals 3 because if we got z equals 2, z equals 4, we kind of guess what z equals 3 would do. Okay. So here is your z equals 1. And here it is, we're coming to z equals 2. So z equals 4. It's got a radius of 2. And z equals 2 and 3 are smushed in here between these two. Z equals 2 about 40% greater radius than z equals 1. And z equals 3 is even closer to this one again. I tried. Here's z equals 2. Here's z equals 3. Contour lines get closer and closer together. Okay. Can you visualize that? Here's the contour lines. Now the slide. Very simple, so you can 1/4 x squared. So you get quadratic around one. And this is consistent with this, because like z equals 1 here. Z equals 1, 2, 3, 4. There's equals 1, 2, 3, 4. You project down to the x-axis, and you see that these projection lines get closer and closer together. You need a bigger line to do that accurately to draw your problem. This thing's getting steeper, so it gets from z equals 1 to z equals 2 a lot faster. Slope gets from z equals 3 to z equals 4 faster than it does from 2 to 3, which is faster than it does from 1 to 2, which is faster than it does from 0 to 1, because it's steep. and you want to relate that picture to this picture. Okay. And you want to then also say, well, it's the same for Y, so chances are it's a paraboloid of revolution. And this kind of confirms it. It happens in the constant C planes. Okay, that's a good start to visualizing what goes on in 3 dimensions. Now, the quadratic surfaces, if they aren't translated, so if you just have X's, Y's, Z's, and no X, Y, even if you have X, Y's, okay. If you have them translated by replacing X by an X minus H, okay. Then, and that simply means you don't have any multiples of X, just X squared, Y squared, Z squared with various coefficients. And then constant numbers. If you have that, then in every one of these planes, you're going to get either a cone, either a circle, a parabola, or a hyperbola. The ellipse, a parabola, or hyperbola. The ellipse might be a circle. Okay. So these things get looking pretty weird. Well, you've done this stuff in quadratic surfaces. You understand, because we've kind of done that with quadratic surfaces. We're saying it can do with any function. These contour lines are called level curves. Now, there's a lot I can say about level curves. One of them is, if we move out radially, this thing increases most quickly. By moving out radially, then in 4 units of, or in 2 units of radius, Z is going to change by 4. Okay. If I move in this direction, 4 units, well, we're going to get another curve out here, but say I'm going to change that much. Okay. This is my direction of maximum increase, radial direction, at any point. So if I want to increase most rapidly here, I do it along the radial line. That's what we call a gradient. If you're in physics, you've seen the word gradient. It's direction of maximum, not just the direction, but the direction and rate of maximum increase. Okay, it comes up. So it's another thing that's really, I think, pretty deep, and it's supposed to support. First place, you're not confined functions of 2 variables. You can have functions of any number of variables. If you've got a function of 3 variables, that's okay. Let's hold the chalk. It's always confused. They gotta listen. Okay, well, anyway, you got a function of 3 variables. You're not going to be able to do a graph like this because you need a 4th dimension, right? So if you got f of x, y, and z, can't graph in 3 dimensions. Okay. To graph it, you're going to have orthogonal axes, and you don't have 4 orthogonal axes in 3 dimensions. You can do orthogonal vectors. Have you gotten to that in linear algebra yet? Orthogonality? No contour lines, but contour surfaces. Okay. These are very important. X, Y, Z equals constant C. Okay. If you set x squared plus y squared plus z squared equal to 1, you have a sphere of radius 1. It's equal to 2, you have a sphere of radius 2. Okay. If it's, I think I said square root of x squared plus y squared plus z squared, I might have said that wrong. Okay. If you set the square, if you set x squared plus y squared plus z squared equal to a constant, you get a sphere of radius square root of c, right? So in one case, you would have like contour surfaces that are just spheres that increase in radius at a constant rate. Okay. Now that's analogous to what we did with 1/4 the square root of x squared plus y squared. If it's x squared plus y squared, then they don't increase as fast. Okay, you have radius square root of 1, or if it's 1/4. Okay, well, square root of 1, square root of 2, square root of 3, square root of 4. You need 3 more to get from 1 to 4. From 1 to 2, from radius 1 to 2. Square root of 1 to the square root of 4. Get from the square root of, to get from radius 2 to radius 3, you'd have to go from square root of 4 to the square root of 9, which would be 5 more steps. It would launch into the same change in radius. Okay. So that's just one example of level surfaces. Now, if you take the left-hand side of a quadratic surface and set it equal to bigger and bigger numbers, you just get bigger and bigger quadratic surfaces depending on the nature of the surface. You get, again, contours. So you can kind of visualize that. Okay, and that's very important. Again, the direction of maximum increase is orthogonal to your contour, And it's real easy to get direction of the normal vector on a level surface. That's very important. Okay, but we've got to get partial derivatives first. Okay,